Okay, welcome to chapter 6, in which we're going to start looking at inverse functions. And so, what we want to make sure is that you had a good algebra experience in terms of a holistic one. And one of the things that they needed to cover was a one-to-one function and its inverse. And so, if you remember, a one-to-one function would have one unique output for every input. And so some of the ways we looked at them was we looked and saw that, oh, you know, they look like this. This is the f of x is equal to x squared. This is not one to one because for two different outputs, it has the exact same y output. That's a problem. One-to-one functions need to be, well, like this line here, y equals 2x minus 1. We know that that crosses at negative 1, has a slope of up to and over 1, and looks like this. That is a one-to-one function. No matter what x you pick, it maps to a unique y, and it passes the horizontal line test, right? And so, is it a one-to-one function? Yes, many things are. But many things are not, even functions that we're well familiar with. And so, if we needed to work with the inverse of a square, we'd have to cut its domain, as you may or may not have seen, but we're going to have to do that here. It says, if it asked me to find its inverse, I don't know if you remember how we found the inverse, but what we did is we took the original statement, y equals 2x minus 1, and we interchanged the roles of x and y. That's what we did to find the inverse, because that's essentially what happens. And then we would solve for y. And so we would get an x plus 1 is equal to 2y, and we would divide by 2, and that would translate to x plus 1 divided by 2 is equal to y. That's what we were doing in your old algebra classes. This, we won't be really finding inverses, but we need to have this idea of things being one-to-one. So let's do some review. A function is a relation to a set of ordered pairs where each x corresponds to exactly one y value. A one-to-one function is where the y value corresponds to exactly one x value, that the reverse process is the same. If f is a function, the inverse of f is a relationship consisting of pairs yx, where xy is an f. If f is one-to-one, then its inverse is a function. The inverse function is denoted by f negative 1, is described as f inverse is equal to the set of all yx's, such that xy is an f. So those are technical definitions. We have this huge warning right here. F to the negative 1 does not mean f to the negative 1. This stands for simply f inverse. So we have to recognize that this negative 1 that's up there is not a power, but the best way that we can denote the inverse. As I mentioned earlier, a function is one-to-one if every horizontal line intersects the graph of the function at most once. And so think about some of those functions we did in the beginning. We looked at the cubic function, right? Is that one-to-one? Absolutely. It's one-to-one. We looked at the absolute value function. Sorry. Was that one-to-one? Absolutely not. Had a bunch of failures in there. We have two different x's being sent to the exact same y. That's a problem. And so we can investigate all those guys. Now, what do we do if we need to work in reverse with these functions? Well, this one's no problem because it's one-to-one, but that one's a problem, and so is this that we saw earlier. Well, what we do is we chop its domain and define an inverse function on that domain. It's what we're going to have to do with the trig functions. And so you're getting into very sophisticated math because you chose majors that have a very sophisticated math need in there. And so this ability to critically think is really important to us. So the four biggies of inverse functions: x and y values switch places. Inverse are reflective in the line y equals x. The functions undo one another. And the inverse function is a function if and only if f of x is one-to-one. And then they go through how to find the inverse. So let's look at what happens here. Find the inverse of f of x equals x squared. This is the one I was referring to, and it's really weird to find this guy's inverse. Well, let's find it the way we're supposed to, and you can see what the problem's going to be. Remember, this is y equals x squared, and to find the inverse from the prerequisite to this class, you are going to interchange the x's and the y's. So this should not be something that you're seeing for the first time. And then you're going to solve for y, right? And that's the process that is described here. Replace f of x with y. Check. Step 2, interchange x and y. Step 3, solve for y. And this solving for y is 100% absolutely positively wrong. If you're saying, well, it's right, Jensen, I took the square root of both sides. You took the square root of both sides, so you must put on this plus or minus. And we don't have a function. If this is a function, for each input there should be exactly one output. And there's not, there's two. So what can we conclude? There is no inverse function for f of x equals x squared. Now, how can we help ourselves? Well, we can look at it on a limited domain. What if we didn't look at the whole f of x? Let me see if that's what they're going to do down here. Okay, no, they're going to do it for sine. So we need to talk a little bit here. So what would we do as mathematicians, right? Or as engineers, or whatever you call yourself? Well, here's the whole function. And the problem is that we have two things being sent to the exact same value. So what would we do? We'd look at only part of it. We'd look at the positive part. So we would consider this function from 0 to infinity. And when we do, it absolutely has an inverse function. Because when you do when you interchange the roles of x's and y, and you solve for y, because you're on the positive part, you know that you're choosing the positive square root. If we wanted the other side, I would go from negative infinity to 0. And we would be on this side. And what would our inverse function be? Our inverse function would be the negative square root of x. Because remember, we've got to get negative values out of this thing. And so that's what our inverse function would be, is the negative square root of x. And remember, it's just undoing that thing. So we're going to define an inverse for sine. They're going to have it below. So the inverse sine, if we consider sine for just a minute, sine looks like this. And it's just like the x squared graph. It's not 1 to 1. We need to cut it so that it is 1 to 1. Just like I cut this one at 0 up here. We need to cut this function so that it's 1 to 1 and obtains all of its ranges values, right? Remember, it ranges from values from 1 to negative 1. Well, where is a good cut? So we cut them always to involve 0. There's infinite number of places where it's 1 to 1. But we need to cut it in a way that's very consistent, because we're going to define this inverse. And this inverse is not just something we're defining. It's the inverse for in perpetuity for the rest of the math that you're going to be doing. So let me show you where we cut it off at. I'm going to grab an eraser and let me change it to a pixel eraser. And we're going to get rid of all this. Right? That's where it's being duplicated. We're going to come right to here. And we're going to come right back to here. This part of the function spans all of the y's of the sine x function and is 1 to 1. So we're going to define our inverse function. On a limited domain for f of x equals sine x, namely exactly what you know. I'll come in here and put it in red, from minus pi over 2 to pi over 2. You want to memorize that. It's going to be right below us in just a minute. So from minus pi over 2 to pi over 2 included. So the important part is to realize that f inverse of x, or sine inverse of x, right? That's not sine x flipped, that's sine inverse of x, can only spit out values from negative pi over 2 to pi over 2. It can only spit out very, very specific values. You could look at that as quadrant 4 and quadrant 1, but it's got to be specific quadrant values. They usually will define it in terms of radians, by the way. I've never seen it actually defined in terms of degrees. And that's because we use it for the arc length and things like that as you move on to different problems. So here's the inverse sine function. The inverse sine function is y equals sine inverse of x, or y equals, they call it arctan, or arcsine, apologize, in this case. They call it the arc as well, because if you remember, it represents, in radians, we represent arc length. Means that x equals sine y for negative pi over 2 to pi over 2 inclusive. So here's some warnings again. Sine inverse of x is not sine x to the power of 1. Or sine inverse of x isn't equal to 1 over sine of x. However, sine squared x is sine x squared, which is sine x times sine x. That's true. So what does arcsine of 1/2 equals theta mean? It means to find theta, and only one. Remember, there's an infinite number of thetas, such that sine of theta is equal to 1/2. Now, what does sine theta equal 1/2 means? It means, if you were to solve this, it would mean to find all angles that has 1/2 as a solution. Now, what is the right angle? Pi over 6 is the only correct solution to arcsine of 1/2. What are the angles that such that sine theta is equal to 1/2? There's a bunch of them. There's pi over 6 in the first quadrant. There's 5 pi over 6 in the second quadrant. And then plus 2n pi. There's a whole bunch of them. Remember doing this before? But there is only one solution to the arcsine, or the sine inverse of 1/2. Pi over 6 only. It can only spit out that. Now, why do we call it arcsine? Because theta in radians is the arc length. If you remember how radians were defined, they were the length of the arc that was swept out. So this is the work that we're doing. Now, is it all? The remainder is to make sure that it sits well for you. They're about to go into cosine and tangent, but let's just make sure that we're okay. Let's talk for just a minute about sine. Sine inverse of root 3 over 2. This angle has to be, so what we're looking for, this is asking for equivalently, what is the angle that lies between negative pi over 2 and pi over 2 that has its sine, oops, not sine like that, apologize. Let me erase a couple of things. Let me put this back to object eraser. What is the angle that lies between, that has, let me get rid of that has. I think there's a better way to say that. Whose sine is root 3 over 2? And the answer to that, we know. It's pi over 3. Pi over 3 by memorization is the angle that lies between those two values, the first quadrant angle that spits that out. If we had sine inverse of negative root 2 over 2, what would change over here? So let me highlight this in blue. What would change over here? What is the angle? So I'm going to come over here and change some things. What is the angle that lies between minus pi over 2 to pi over 2? Whose sine is, and the only thing that changes, negative root 2 over 2. Well, we know that guy. That's a 45-degree angle. That's a pi over 4 angle written between negative pi over 2 and pi over 2 only. If you tell me 7 pi, if you tell me 15 pi over 4, well, not 15 pi over 4, they wouldn't say that, apologize. If you tell me 7 pi over 4, and it's wrong. And you'll say, I don't get why it's wrong, Jensen. 7 pi over 4 is a fourth quadrant angle, and so is negative pi over 4. We're not dealing in a circle. We're dealing in a function. And here is minus pi over 4. And here is the negative 7 pi over 4 area. They're not the same value. These are two different y values, or two different x's that are putting out the same y value. You have to spit out the one that's between these two. My question to the person would simply be this. Where does 7 pi over 4 lie? Does it lie within negative pi over 2 to pi over 2? Think about it as a number line. Here's negative pi over 2. Here's 0. Here's pi over 2. Where's 7 pi over 4? Well, it's way down here. Well, that's not in that interval. It's got to be between here. So what's in between there? The minus pi over 4 is in between there. It's the only one. So you're going to have to just be disciplined and remember that discipline. Again, they're not trying to do anything more than get us to think critically so that we can be successful in future classes. And they're using trig as a tool. Cosine's not one-to-one on its domain as well. Remember what cosine looks like. Cosine looks like this. Okay. So we'll always cut it so that we span our regions from, let me put the line right there, 1 to minus 1. So how are they going to cut cosine? They're going to cut it right like this. They're going to cut it. Cosine's different. They're going to cut it from 0 to pi. They can't cut it from minus pi over 2 to pi over 2, or they would have. They cut it from 0 to pi. And so that's the conditions for this guy. So the if f of x is equal to cosine inverse of x, then those y values have to be between 0 and pi. So what's the cosine inverse of 1/2? We've got to think for a minute. Well, what angle tells us the cosine is 1/2? What cosine of what angle is a half? Well, pi over 6 cosine is root 3 over 2, so it's pi over 3. And we're finished. That's between there. We're just looking for that first quadrant angle, but be careful here. What if it was negative 1/2? A common mistake is to say negative pi over 3, but that's not true. The cosine of negative pi over 3 is actually positive 1/2. It's right over here. And it's not even true, and it's not within our range. And so we don't say that. What do we need to name? So we're getting out of this that we need to, this right here, that we need a first or second quadrant angle. Since it's negative, it's not going to be a first quadrant angle. It's going to be a second quadrant angle. What angle is that? 2 pi over 3. Pi over 3 back from pi. And we get really, really good at this. How about inverse tangent? If we look at the tangent function, here's what you remember about tangent. It has some asymptotes. And right here in the middle, it's 0, and it goes up. Oh, apologize, doesn't look like that at all. It's coming from up and then goes down and then just repeats that. So that's what they're going to pick. They're going to pick the 0 to pi over 2, right? And so it's going to be defined on, um, oh, I apologize, that's not tangent. You must be thinking I'm crazy. I really apologize. I was drawing cotangent, and I knew that that was a problem from what I was about to say. Let's go look at this for just a minute. I had the pi over 2 right, but if you remember tangent, and I really apologize for the misleading you there for a moment, it's from minus pi over 2 to pi over 2. It reaches 0 right in the middle when sine 0 and goes up from there and goes down like that. So apologize, I was a little bit confused in what I was trying to write. This is better. Has a period of pi. This will be the segment that they pick from minus pi over 2 to pi over 2. But I hope that you see I have something wrong there. I hope that you see that these guys are wrong. They should not be squared off brackets because that's where tangent's undefined. They should be rounded brackets. But what's nice is tangent shares the same thing for sine. So if you remember, sine was from minus pi over 2 to pi over 2, and so is tangent. Remember what tangent theta is. Sine theta over cosine theta. Its top wins. That's who he behaves like. So guess what about cotangent theta? When it's cosine theta over sine theta, guess who wins? Cosine. And cotangent is from 0 to pi. So there'll be some connections like that. You want to memorize these restrictions. You absolutely, positively want to memorize those restrictions. Sorry. Let's get to where we're at. Okay, so it erased what I was doing. So inverse tangent. So here's the summary right here, and then we'll end this video. The cosine inverse function spits out values, shouldn't have a minus there, from 0 to pi. So this right here should just be 0 to pi. The tangent from minus pi over 2 to pi over 2. And then they're going to give us the cotangent. So notice cotangent corresponds, that should also be 0, to cosine like I was just mentioning. Secant's 1 over cosine, so it's going to have the same restrictions as cosine. And cosecant's 1 over sine, so it's going to have the same restriction as sine. So there's some good things in here. The inverse secant and inverse cosine functions are sometimes defined with different ranges. We use intervals that match those of the cosine and sine, except for the missing points, right, that are in there. That'll happen. So what are we recognizing? That the range of sine is quadrant 4 and quadrant 1. The range of cosine is quadrant 1 and 2. The range of tangent is also like sine, 1 and 4. I'm going to just list them in different orders. It doesn't matter what orders. Cotangent has cosine up top, so it's going to be 1 and 2. Secant is going to be between secant's going to be just like cosine, right? So it's going to be 1 and 2. Now notice it's being split at the pi over 2. That's because it has an asymptote there. And cosecant is going to be 1 over sine, so that's going to be 1 and 4. Now the key part in this is that these angles here that are quadrant 4, they all are represented the same as a negative first quadrant angle. Okay, so let's take a look at these questions in the next video. Consider the inverse cosine function. Is the function increasing or decreasing? I think these are important right here. These ones that we're going to be looking at next. And so this will mirror the problems that are here in 6.1 as they're trying to get us used to this type of